This will serve many purposes. We're going to look at some pictures of things in space. First, we'll look at the whole sky, but then we'll start nearby and work our way out through the universe. And we'll look at things in the radio and in the optical, since those are the two that we've covered so far, to try to convey that it's often very, very different what you see in the radio compared to what you see in the optical, and it tells you different things. As we go along, we'll talk about some new emission mechanisms. We talked about thermal before, absorption emission lines due to atomic level transitions. We'll throw some more at you. But first, before we get into that, I want to talk about this picture here. It's an example of what many of the radio pictures will look like. This is a false color image. This one was actually taken in the infrared by an infrared camera. But the colors are false. It was a black and white camera. And often in the radio, not always, but often in the radio and other wave bands, it's black and white. For example, here you have a person who's holding a match. And it's taken in the infrared. So the hottest thing is going to be the match that this person's holding. The next warmest thing in the image will be the skin. The skin's warmer than the air around you. And so in this particular image, they chose to make the brightest thing white, the next brightest thing red. After that, you see he's wearing a tie like I am. The tie is off the body. It's a little bit cooler. Glasses like I am, off the body, a little bit cooler. So you get the greens and the blues. And then the air in the background is the coldest thing in the image. And so it's blue and black. But I could have chosen a completely different spectrum. If you played in Photoshop or some similar program, you understand this. I could flip all the colors around. I can make a green, purple, yellow, whatever combination I want. And so we call these false colors. You shouldn't interpret the color too seriously. It's a way of indicating brightness. Sometimes the colors are genuine, and I'll point that out when it occurs. Okay, let me kill the lights for this so you can see this as good as you can anyway. Okay, that's pretty good. So let's start with the optical sky. This is a full sky map in the optical. The way it works is imagine taking the left of it and the right of it and pulling it around your head and connecting it. And then take the top of it and the bottom of it, pull it around your head and connect it. Of course, just chop your head off, but that's technicality. That's the basic idea. That's the full sky. The sky is all around us, but you can imagine cutting a seam and flattening it and putting it on the screen. That's what it's like. There are distortions. You can't put a spherical image onto a flat screen without distortions. It was cut open and pasted here in a particular coordinate system called galactic coordinate system. In that coordinate system, the center of the galaxy is at the center of the image. That's the center of the Milky Way galaxy there. And the plane, the disk of the galaxy, runs across it. So I think I mentioned before, we live in a galaxy, we call it the Milky Way. It's a collection of stars and dust distributed kind of like a flat pancake with a kind of a bulge at the center. We live in the pancake, often the outskirts. So you can imagine sitting there in the pancake looking around. If it's a semi-transparent pancake, you look up, you're going to see out. If you look down, you're going to see out. But if you look into the pancake or all around it, there you're going to see a lot of pancake, right? And so that's what we see here. We see a lot of stars going across the center of the image, but not as many above and below. The stars above and below are nearby to us. You can't see distance, but just the way the geometry works out, those are for the most part nearby stars. Though some of those points above and below are distant galaxies, whole collections of stars in their own right. But looking into the plane of the galaxy, we see a tremendous amount of stars. You can see color. I told you there actually is color in space. It's just when we look at it, the light levels are too low, so our rods kick in, and our rods are black and white. But if you take it with telescopes, with the filters, and combine it all, and then project it up here with a greater intensity so your eyes can see the color, there it is, and you see there are all sorts of blues, which are the new stars. And then you have these black regions going across it. Any idea what that black stuff is? What's blocking the light there? Gas? It's something in the gas. It's actually dust. Dust is very good at blocking visible light, blue light in particular. The redder you go, the easier of a time it has getting through. Those are longer wavelengths. If the wavelength gets longer than the dust, it can pass through. If it's smaller than the dust, it can't. And so the blue wavelengths are really short to get blocked by the dust. But once you get into the infrared and the radio, it passes through. There's the first of many differences between the radio and the optical. We can't see what's going on in the plane of the galaxy, in the center of the galaxy, because there's so much dust embedded in the clouds of gas. It's blocking our view. But in the radio, those long wavelengths, they'll go straight on through, and we can probe those regions. Got some other interesting things in this picture. If we look over here, this little spiral, that's Andromeda. That's the nearest big galaxy to us. Probably looks a lot like our galaxy, but you can see how far away it is. Here you have the Magellanic Cloud, so large Magellanic Cloud and a small Magellanic Cloud. These are little baby galaxies, dwarf galaxies that orbit the Milky Way in close proximity. You can't see them from the northern hemisphere. You have to go to the southern hemisphere. Has anyone ever been to the southern hemisphere and seen these? Now, if you go down there, whatever town you're in, get out. You get out away from the light and into the darkness and look up, and they'll be there. Well, if it's the right time of year and all that. But they just look like clouds, except the other clouds are moving across the sky, but those kind of just move with the stars. That's why they're called Magellanic Clouds, first identified in the west anyway by Magellan. And then you have this little cluster of stars over here that you've all seen, whether you knew it or not. These are the Pleiades, the seven sisters. You might have seen up in the sky a little concentration of stars. There's 7 of them there, and that's visible from the northern hemisphere. Okay, anyway, this is the picture of the universe, and, we just spent like 5 minutes talking about it, but in ancient times, before all this light pollution and civilization and tall buildings, everybody would have known that. I wouldn't have had to spend the 5 minutes to explain what these things are. Let me just ask you, how many of you, and don't be shy about this or ashamed or anything, how many of you have never seen the band of stars going across the sky, the Milky Way? It's okay. Okay, that's good. You got to see this thing. It's amazing. And you can do it from here on a clear night with the moon down. So a moonless, clear night. Just get out of Chapel Hill. You don't have to drive far away. Go to Jordan Lake or something. You get out of the car, turn all the lights off, give your eyes 10 minutes to adapt to the darkness, and look up, and you'll see this amazing band of stars going across the sky. That's this band of stars going across the middle, the Milky Way galaxy. So you can see it, but now many of you haven't, just because the modern civilization we live in, the skies are bright, and we live in population centers that are extra bright as well. But back then, everyone would have known this, and there's this idea going up through the centuries that the universe is this kind of calm, unchanging place. We saw this when we talked about the geocentric universe. There's this idea that anything changing in the sky had to be atmospheric, because they literally thought the universe was completely eternal and unchanging. Calm, serene. And we really had this idea right up until the birth of radio astronomy, when we realized that, wow, the universe is a busy, happening place. A lot of the sources in the radio change their brightness by a factor of 2 or more on timescales of days or months. Some are steady, but there's a lot of variability outside of the optical. And the optical, it tends to be pretty steady, except for occasional supernova here or there. Some stars vary at like the 1 or 2% level. In the radio, it's a big, busy, happening place. Here's a radio picture. Same coordinate system, full sky. Colors are false, so don't get hung up on the colors. Same color scheme as before, where white means bright, and then red and yellow, orange, blue, purple, black means dim. But we see it looks different. You're probably already starting to notice some of the differences. But the first one I'm telling you, you can't see from this image, is this is a changing thing. Most of the points here are brightening and dimming, many of them anyway, on interesting time scales, unlike the optical. It's a violent, explosive place, the universe. And that property tends to come out in the radio. And let's see some of the differences here. You see, there's the optical, here's the radio. What are some of the things you notice that are different? Anyone want to shout out? One difference. Heard something back here? It has a hat on. Yeah, there's this thing sticking up over the top of it. That's called the North Polar Spur. And you don't see it so much in the optical, though it's quite bright, noticeable in the radio. The thinking is, when the galaxy formed, the galaxy was this big cloud, and it collapsed down to a disk. And when it collapsed, that triggered a tremendous amount of star formation that blew out a lot of gas above and below the plane. You got to envision it as an expanding bubble off the top and the bottom. It's most noticeable in this one extension here. Right here. When you had the star formation that made a whole bunch of hot stars, it warmed the gas around it, the big stars exploded in supernovae. So all at about the same time, a tremendous amount of energy was dumped into this gas, and it blew open these bubbles above and below the plane that you only see in the radio. What's another difference? What about the number of points? We saw a number of points in the previous image. What were those points for the most part? Stars, yeah. You don't see so many points in this image. There are points there, but not nearly as many as the previous image, point sources. Flip back one time so you can see it. Stars, they tend to have black body spectra that peak in the visible and maybe the ultraviolet or infrared. Down the radio, they're still emitting, but not as strongly as near the peak of the thermal spectrum. And most of them are far away, so in the radio, unless you look really hard, you don't see stars. And that's a big difference. In the optical, you go out at night, mostly what you see is stars. In the radio, the only star we really see easily is the sun, and that's only because it's so close to us. Certain stars you can pick out in the radio, but for the most part, no stars. Most of the sources that we're looking here are something else. We can see some of the things that we saw. We see the Magellanic Clouds. Here's the large, here's the small. Andromeda is actually this faint disk here that's hard to see. But most of these points, like here, 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 etc., and all around, are violent processes. Exploding stars, supernovae, star-forming regions, so stellar nurseries, and supermassive black holes in the cores of distant galaxies. Those tend to be the big emitters in the radio sky. Okay, one last big overall map, and it will introduce the first of our new emission mechanisms, which is the 21 centimeter emission line, called H1. A number of you have been asking about that in the homework. H1 refers to neutral hydrogen. Cold. Neutral, cold hydrogen. H2, just for reference, H2 is ionized hydrogen. Now, what we're looking at in this map is all radio wavelengths, well, not all, but a band of them turned together. We narrow in to just one specific wavelength, 21 centimeters. It looks very different. This is an emission line in the radio. I'll explain how it works in a second. But you can see here in this image we have point sources. We have the North Polar Spur. Over here we don't have hardly any point sources. We just have gas in the plane of the galaxy. And if you believe me for a second, I'll explain the process in a second, but if you just believe me that at this wavelength, it's only being emitted by cold neutral hydrogen, it shows you where the cold neutral hydrogen is. It's in the plane of the galaxy. And all these other sources are not cold neutral hydrogen. They're, as I said, hot, explosive, violent processes. So how do we get this 21 centimeter emission line? To understand this, it's an emission line, 21 centimeter emission line. Now we've talked about emission lines already in the optical, infrared, and visible due to atomic transitions. If you're hopping from here to here, here to there, that gives off an emission line. It gives off light, and it tends to be in the infrared, the visible, or the ultraviolet, because these are big energy transitions, and so you get these high energy photons. Radio, low frequency, low energy. So the 21 centimeter emission line is very low energy. Lower than you're going to get from any transition between orbital levels. So this is a really subtle effect. It occurs just in the ground state. So we have the proton, we have the electron, orbiting around. I'll drop twice. The proton and electron, they're not just sitting there, they're spinning. And if you have spinning charge, we hinted on this before, but you'll see it on all scales really soon. If you have spinning charge, what do you get? If you have moving charge going in a circle, you have a current. Whenever you have a current, you get perpendicular to it a magnetic field. And you'll see this on scales of supermassive black holes and now on the scales of little particles. These are like little bar magnets, where you can have a north and a south, north and a south, or you can have the opposite configuration, where this is north-south and this one is south-north. I wish I had my bar magnets. I thought I had them with me. But you've all played with bar magnets before. There's two bar magnets, and if you put them together, there's one configuration in which they're happy, they stick together. But if you flip it around, they fight against you. They don't want to go together, right? You all understand what I'm talking about? If you take the two bar magnets and put them together, the poles align, north here, north to north, south to south, they repel one another. They don't like that. They push apart. It takes energy to hold the bar magnets in that configuration. If you flip one, they attract to each other. So let's draw that. Here's flipped, north to south, south to north. They're pulling towards one another, so it takes less energy. They want to go together that way. They don't want to go together the other way. The hydrogen atom, cold hydrogen, with the electron in the ground state, meaning it's cold. Same deal. It's going to take energy. This takes extra energy. This takes less energy. The bar magnets like to be held together this way. They don't like to be held together that way. So if you have hydrogen out there in the universe, just bouncing around, bounces into things, every now and then it can be collisionally excited into this state. It doesn't take much energy. It takes just a little bit. So collisionally excited to here, and then it transitions to here, releasing a very low energy photon whose wavelength is 21 centimeters. That's the 21 centimeter emission line. Now, if you get a hydrogen atom in that excited state, it will stay there typically for about 1 million years before it decays. It's a random process, sometimes faster, sometimes slower, but about 1 million years. And it seems like a long time, but there's so much hydrogen in the universe that you look at any patch of it, cold hydrogen, you're going to get a lot of emission at 21 centimeters. And that's what we're seeing here. Just cold hydrogen bumps into each other, excites, and then after 1 million years it emits that 21 centimeter photon. Not necessarily the most exciting process in the world. A supernova explosion, much more exciting. But this is a good way to figure out what's going on physically. And you don't have this in the optical. In the optical you have these transitions. In radio you have these. And this tells you where the cold hydrogen is. So the North Polar Spur, is that made of cold hydrogen? No, it's not. So automatically you can distinguish between. Okay. Let's start working our way through, and we'll keep track of the emission processes as we go. But before, we did thermal. We've done optical, including infrared and ultraviolet emission lines. Here's the H1 21 centimeter emission line. Again, it's a way to shake a charge. If you take that electron, you flip it, you just shook it. So you're sending a ripple through the electromagnetic field, and you have light, radio light. Okay, we're going to start working our way through the solar system, starting very nearby, working our way out, and then out to the edge of the universe, looking at things in the radio and the optical. Anyone want to guess what we're looking at here? The moon. That's right. This is the moon. Very nearby was the hint. This is the moon in radio. Again, it's false color, but if you look past that, you can see that it's brighter on the left than it is on the right. So what do you think that is, being brighter on one side than the other? The sunlight, the reflected sunlight, the phase of the moon. So that's right. Most of what we're looking at the left is reflected light from the sun. It's the phase of the moon. What's interesting about this is the part that's not reflecting light from the sun, the part that, on the dark side of the moon. We're still getting radio light from there. So that over there is not reflected emission. So we have two things going on. We have reflected light, and then we have it emitting its own radio waves. Any idea why? It's one of the processes you're familiar with. Thermal. Yeah, it's not cold hydrogen, because the moon's not made of cold hydrogen. It's thermal. The moon has a temperature. It's about 220 degrees Kelvin, typical average temperature. At least the distance slightly below the surface where the radio waves are coming out. But it has a temperature, so it's going to emit thermally. So the moon falls into this category. So if I ignore the reflected light and just measure the brightness over there, I can actually compute the temperature of the moon without having to go there. So again, it's a diagnostic tool that in the optical, we can't do that. We can't look at this picture and know how hot the moon is. But we can look and measure this picture and figure out how hot the moon is. So here's the optical picture of the moon. I like put it out there because it's kind of a nifty picture. You'll never see a picture like this. When you look at the moon, what do you not see around it? Stars. It's because your eye's adapting. The moon is so incredibly bright, it adapts to that brightness level, and you don't see the faint stars around it. When you take a picture of the moon, you got to do a short exposure. And in that short exposure, you can't see the stars. So this is a fake. It's a composite. Someone took a long exposure of stars and pasted on it a short exposure of the moon. It's the same reason when you look at pictures of astronauts on the moon. You know, the naysayers, they're like 1% of the population who's crazy. Says we've never been to the moon. They say, look at the astronauts in there. There are no stars. But there's no atmosphere. You should see the stars. Well, to take a picture of the astronaut without overexposing your camera, it had to be a short exposure because he's illuminated by the sun. In that short exposure, you don't get the stars out. Okay, next object. What's this? Farther out? That's the sun. If you had radio eyes, that's what the sun would look like. Two emission processes. Again, it's false color. The blue haze all over the place. That's thermal. The sun is hot, and so it has a thermal spectrum. It has a radio tail. It's emitting radio, just like you all. You're emitting radio. So it has a thermal component that you can measure and get the surface temperature of the sun, 5,800 Kelvin. But on top of it, the really bright part of the sun are these spots. Any idea what they are? Those are sunspots. And this introduces a new mechanism for us called synchrotron radiation. Very powerful way to produce radio waves. Synchrotron, which means magnetic fields are involved. Sunspots, now in the optical, they're dark. Right? We look at the sun in the optical, those are the dark spots, the sunspots. In the radio, they're bright. That's because sunspots are regions of intense magnetic activity. In the optical, that magnetic activity is actually impairing the flow of energy to the surface. Now, energy is created at the core, it works its way up the surface. But if there are magnetic fields threaded through the surface, it can impede that flow and make a cold spot. But if you have the magnetic field there, let's say here's the surface and we have a magnetic field coming out. Electrons can get caught in that magnetic field and they spin around it. Just like a spinning charge or a cycling charge makes a magnetic field will make charges cycle around it or circle around it. And so if electrons get caught in these fields, they're shook round and around and around and around. And whenever you shake a charge, you're sending ripples through the electromagnetic field, you're making light. And that's what synchrotron radiation is. It's a continuum. So it's not a line. These are lines. But this is a continuum. This is a continuous process, a continuum process. Emits at all radio wavelengths and even higher, sometimes into the optical and even the X-rays and gamma rays. But it looks different. It's a different shape spectrum. We won't go into it, but it's caused by electrons being shaken by the presence of magnetic fields. There's the sun in optical. What's this? Anyone want to guess? It's not Andromeda. It's much closer. It's a good guess, but that's not it, actually. Jupiter. It's Jupiter. People think Saturn, they think the rings. And so Jupiter has the strongest magnetic field in the solar system. Charges are thrown off the sun, they work their way out, and they get caught up in Jupiter's magnetic field, and they spin around the magnetic field lines, illuminating the magnetic field. Jupiter kind of sits in the middle. You can't see it. It doesn't emit enough thermal radiation in the radio. The magnetic field and the synchrotron emission dominates. So we look at Jupiter in the radio, and we learn something completely different. We don't see clouds or moons. We see the magnetic field pattern. And this is kind of a side view of it, but you can image it time after time and turn it into a little movie. What we have here, you have this triple banded structure. Above and below are pockets where radiation gets trapped. We have similar structures in our magnetic field on Earth called the Van Allen belts, where you might or might not have heard of them, where particles can get trapped. The one in the middle is unique to Jupiter. Anyone have any idea what's orbiting there? I can't give it orbiting. It's a moon. Anyone know which moon? Io. Io moves within Jupiter's magnetic field, constantly disrupting it, and spewing new particles. Io has lots of volcanoes, and those volcanoes spew particles that get trapped in the magnetic field, illuminating that band there. So in the radio, it's a completely different place. It looks completely different than it does in the optical. And there it is in the optical. There are other ways to get radio waves out of Jupiter. Pummel it. Anyone remember Comet Shoemaker-Levy 9? It was 94. You probably don't remember. You might have read about it. So this comet passed by Jupiter some time ago and got so close it was broken into fragments. Next time it came back around, it was actually on a collision course. It impacted the planet. And so when it hit the planet, it made hot areas that glowed in the infrared and the radio. And it hit piece by piece. So here's an infrared picture. You can see the impact zones down here. Boom, 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 boom. And what we have right here, what's this glow? The impacts on the backside. We couldn't see them directly. The way we studied them is when it hit, it would often reflect light off of the moons. This is one of the moons coming up over the surface of Jupiter, reflecting light from an impact. And afterwards, it glowed for months because of its extra temperature. So it's thermal. Anyone want to guess what object this is? Saturn. Yeah, you all thought the last one was Saturn, but this one's actually Saturn. Saturn, compared to Jupiter, has a very weak magnetic field. So when we look at Saturn in the radio, we're actually seeing thermal. The magnetic field's not strong enough to shake those electrons enough to flesh out the magnetic field in the radio. So we're seeing right down to the surface of the planet, and we're seeing the thermal emission off the surface, just like off the moon. So we can measure the temperature of Saturn this way. The temperature of the rings, you see there's less emission coming off the rings. And interestingly, if you look at where the ring passes in front of the planet, it is blocking some of the radio. And you can block if you're the same size or bigger than the wave. So radio waves can be quite large, anywhere from centimeters to meters. So depending on what wavelength you look at, and depending upon the sizes, the chunks of ice that make up the rings, it blocks more or less. If you're looking at long wavelengths, the big chunks will block those. If you're looking at small wavelengths, only the small chunks of ice block them, and the rest gets through. So by looking at Saturn at different radio wavelengths, we can figure out the sizes of the chunks of ice. Here, they might be only this big, and there's no way we can see it from Earth or even in Saturn orbit. From this radio analysis of what gets through, we can figure out the size distribution. Again, that's something you cannot do in the optical. This is a picture of Saturn in the optical. Okay, moving out of the solar system, I'll show you some things that are going to become less and less familiar, but some of you might be able to recognize this. What is this? It's the, close, it's the Orion Nebula. Eagle around here somewhere in this part of the sky. This is the Orion Nebula, and this is a star-forming region. It's a stellar nursery where stars are born. What you have here is a big, massive cloud. You can see the edge of it here. This is the edge of the cloud. And the cloud continues off the screen way, it'd be across the room to scale it. There's a giant, relatively nearby cloud of cold hydrogen gas and dust floating in space, getting close to us. But on the edge of the cloud, and other locations around the cloud too, the surface has been disturbed. What happened is some time ago, a star over there exploded and sent a supernova shockwave that bounced up against the cloud, compressing it. And when it compressed this gas, it triggered new star formation. So these are new stars. A handful of them down here, and another little one up there. And these new stars, you have a whole bunch of different stars, some really massive, some low mass. You get a whole distribution. They all form together. The most massive ones spit out the most energy. They're the most luminous. They spit out the most energy. And those most massive ones are energizing the region of space around it, ionizing it. So the cloud itself is cold gas, way over here, away from these stars, H1. But right around these stars, that's H2. That's ionized gas. Go back here, H2 is ionized gas. Those stars are spitting out ultraviolet photons. They're enough to knock the electrons out of the atoms, giving you this very hot, very ionized gas. And what it does, hot gas tends to what? Expand. And so here, I'll draw a picture of what you're seeing there. Here's the edge of the cloud. Here you have the new stars, and it's heated, this bubble, and this is hot, H2. Over here we have cold, H1. and it's expanding and pushing back into the cloud itself. So right here, the interface, we get a region that is hot and dense, which brings us to our last emission mechanism. So the last mechanism, and I'll stick it right here, something called Bremsstrahlung, another German word, 2 S's, Bremsstrahlung. You get this if you have a hot, high-density gas. And the mechanism, again, if you want to get light, you've got to shake charges. And it, too, is a continuum emission. Imagine in this hot, high-density region, if we zoom in, since it's high density, the particles are going to be bouncing into each other quite frequently and zipping around each other. It's kind of like thermal. But here we have a charge. Maybe it's a negative charge, and here's a negative charge. And they're zipping past one another. As they get in close proximity, they bend each other's paths. Negatives and negatives repel. Or you can have a positive and a negative attracting each other, and they kind of whip around each other. I don't know how this would go. Kind of like this, I guess. But if you have this really hot distribution of particles, and it's dense enough that they're bouncing off each other due to the charge interaction, you get Bremsstrahlung. There's no magnetic field shaking the charges, just their own inherent charge is deflecting each other's paths. And again, when you move charges around, you deflect charges, then you're going to be shaking the electromagnetic field, and so light will be emanating from these interactions. That's Bremsstrahlung. So H1, we said this corresponds to cold hydrogen. Bremsstrahlung, you get this if you have hot and dense hydrogen. Synchrotron, you get if you have magnetic fields. What's this called? Anyone familiar with this object? Crab nebula, that's right. So it's also called a nebula, but physically it's a completely different process. This is the other end of stellar life. We just saw star birth. This is star death. So this is a supernova remnant. This is the Crab supernova. It went off in 1054, I believe. It was close enough that it was bright enough to see during the daytime sky for many days. And it was a very bright object during the nighttime sky for many weeks, if not months. It was noted by astronomers all around the world, Middle Eastern astronomers, Chinese astronomers, Native Americans carved it into the rock. European astronomers seem to have missed this. There's no record of European astronomers noticing the daytime star. But, oh well. And so supernova remnants are an example of synchrotron radiation. When the star explodes, all stars have magnetic fields. Our sun has magnetic field. And if you have a massive star, it will explode. And that magnetic field is carried out with the materials. It's entwined with the materials. And so, in this case, you had a rather complicated explosion. Some explosions are simple, nice spherical expanding bubbles, with the magnetic field weaved into the expanding bubble. Here, the magnetic field dominated and redirected the flow into this tangled mess. And what you see, where you see emission, you are actually seeing a magnetic field confinement. And so this is kind of an optical picture. The radio picture looks very much the same. Again, you get this kind of messy explosion, and the radio waves are coming from where you have the magnetic fields intertwined with the material, so it's synchrotron radiation. Here's another supernova remnant. This one's called Cassiopeia A. We used to think it was the last one to go off in our galaxy, but we recently found another one. So this is the second to last star to explode in our galaxy. It went off 320, 330 years ago. 330 now it is. And about 1680 is when we think that it went off. But it was never seen because it was deep down in the plane of the galaxy where you have the greatest concentration of gas and the greatest concentration of dust. If you remember back to the optical image of the galaxy, we have those dark lanes, the dust lanes. Bring it up here. Here, where the dust is just so concentrated we can't see into it. And that's where this supernova went off. So when it went off, nobody actually noticed it. It was maybe picked up by one guy who was cataloging all the stars in the sky and picked up this strange faint star that was never seen again. Flamsteed might have actually picked this up and never realized it. But it wasn't noticed by the masses, and it was rediscovered by Groth-Reber in the 1940s. Jansky might have seen it, but he didn't really know what he was looking at. But in the 1940s, it was rediscovered as one of the brightest radio sources in the sky. So again, a big difference. In the optical, we see nothing, but in the radio, it's one of the brightest things in the sky. This bubble is expanding by about 1% per year. It's so new, so recent, that you can still see it expanding by about 1% per year and fading by about 1% per year. Okay, this is about as deep into the galaxy as you can get. Anyone want to guess what this is? A black hole. There is a black hole there. Jansky was the first to see this. So the constellation is Sagittarius. This is called Sagittarius A. In the optical, we name stars Alpha, Beta, Gamma, like Alpha Centauri, Beta Centauri, Gamma Centauri. They're brightest and getting fainter. In the radio, they're called A, B, C. So this is the brightest thing in Sagittarius in the radio, Sagittarius A, and it is the center of the galaxy. It's another example where in the optical, we can't see it because it's behind all that dust. There's no hope of ever figuring out what's going on there in the optical or visible part of the spectrum. But in the radio, the waves are much bigger than the dust particles, and they just go right on through. And we see this kind of interesting structure. It's throwing some stuff out, and there appears to be some kind of a whirlpool there down at the base of it. So let's zoom out for a second. Here's the plane of the galaxy in the optical, and you can see it's dark right there in the middle. Here's the center of the galaxy. But if we go to the radio, look at the dark band, it becomes the bright band. So here's what the center of the galaxy looks like in the radio. You see through all that dust, and it's a busy place. There's all sorts of stuff going on. There are a lot of stars there, so a lot of stars have exploded. So these are supernova remnants, these expanding bubbles, H2 regions, those are stellar nurseries, and often they're right on top of each other, because the star is born there and then it dies there. Sometimes the time scale can be rather quick. Anyway, at the center you can see Sagittarius A, that blob with these wisps coming out of it. And this is what we think is going on. There's lots of lines of evidence that go into this, and a lot of this is done in Astro 102 if you take it. But we think there's a black hole there, a massive black hole. We call it a supermassive black hole, about 1 million times the mass of our sun. Or maybe it started off as a small black hole, and over time it just absorbed so much material. It is at the center of the galaxy. It's the densest part. And stars will get too close to it. As a star passes by too close, it will get torn apart and form a disk of material around it. The thing's constantly being fed by stars in the vicinity. Getting too close, gas being torn off it. It continues to grow. And over the, probably 10 billion years that the galaxy's been around, it's gotten up to about 1 million solar masses. And we observe other galaxies too. We actually think this is kind of the standard picture. There's nothing unusual about 1 million solar mass black hole at the center of the galaxy. So you can see the black hole part in the middle. It's dark. This is, of course, just a drawing. But this dark region here where even light can't escape, that's the defining characteristic of a black hole. But around it we have this disk, and we call it an accretion disk. Again, in this case, it's torn up stars working their way down into the black hole. But it's very hot in this disk. All this gas bouncing into each other. It ionizes it, and so you have charges going around in a circle. Whenever you have charges in a circle, what do you get? Perpendicular to it, a magnetic field. So just like when we were talking about the electron, the proton, a little charge spinning in a circle, generating a magnetic field. Here it is on a much larger scale, many solar systems across, charges going around a circle, making this huge magnetic field. So not all of this material will find its way to the black hole. Some of it will get caught up in this magnetic field before it falls into the black hole, and then it's shot out of the vicinity at high speed. It'd be about 10% the speed of light. The expulsion material, we call that a jet, an astrophysical jet. It's magnetically dominated, and so as the charges, the electrons work their way out in the jet, they're spinning around the magnetic field. So you get what kind of radiation? Synchrotron radiation. And so that's what we were seeing in the previous image. Let me zip back to it. Here it is. The material being thrown out is emitting synchrotron in the radio. Here it is. It goes a little distance out before it gets redirected just by the flow of gas in the vicinity. So it doesn't make it too far. Okay, moving up farther. We're now outside of our galaxy. This is a radio picture, looking at the closest large galaxy to us. So any idea what this is? Andromeda. This is Andromeda in the radio. Now, a lot of the dots are stars in our own galaxy. We have to look kind of through our galaxy to see Andromeda. So a lot of these are nearby objects. But if we look past them, the thing that's far away is that ring of material. And that ring, I'll just say that this image was made at 21 centimeters. And if you look at any other wavelength, the ring disappears. So what is that ring? H1. It's cold hydrogen gas. Emission line just at that one wavelength. Look at any other wavelength, you don't see it. It's invisible. So that tells us cold hydrogen gas. But the central blob, it turns out it's moving with the galaxy. We can test the Doppler shift. As a continuum, it's there at other wavelengths. And so, if you had to guess, what do you think that is? Or what do you think the object is, first of all? Black hole, yeah, a supermassive black hole. The emission that's coming out of it is consistent with what our central black hole would look like at that distance. So it's probably about 1 million solar masses, and by synchrotron radiation. And that's Andromeda in the optical. Again, it looks very different depending upon the wavelength, but you learn different things. And you can see the little blobs, those are little dwarf galaxies that orbit around it, like the Magellan Clouds orbit around us. Okay, as we move farther out, there are, of course, many, many, many galaxies. But I'll just highlight a few. And these are ones with billion solar mass black holes. Most galaxies, like ours, like Andromeda, have 1 million solar mass black hole. But every now and then you have one that formed a little bit early, ate a lot of material. Maybe the galaxy collided with another galaxy, which tends to throw a lot of material towards the center, feeding this black hole. And you get billion solar mass black holes. This one here is called Centaurus A. It's in the southern hemisphere. And this is an optical image. And it's a weird-looking galaxy. It has dust going around it. But the rest of it is kind of random and chaotic. And what we think happened here is you had a collision of galaxies. Galaxies actually can run into each other. So we talked about on the second day of the course, the distance between stars is immense compared to the size of the stars. Two galaxies collide, the stars go right past each other. The distance between galaxies is not that big compared to the size of the galaxy. So you can have galactic collisions. The gas does actually run into each other. The stars pass through, the gas collides. So this looks like a recent collision. The galaxy in the interior part's all jumbled. You still see dust left over from probably one of them, a spiral galaxy. But this has made the black hole in there bigger and more active. Now, suppose that the central black hole is spinning kind of like the spiral galaxy was, in this direction here. Which direction do you expect the jets to be going? Perpendicular. It's not necessarily going to be exactly that because it is a messy collision, but here a radio contour is superimposed. And so, yeah, it is perpendicular. Look at the scale of these jets. They're bigger than the whole galaxy. So that's what happens if you have a billion solar mass black hole. The expulsion of material can be not just in the center of the galaxy, but completely out of the galaxy itself. So the contours of the radio. Powerful, powerful process. And you would totally miss it just by looking at the optical. You never know what's going on. In the radio, that's all you see. You don't see the other parts, the stars or the dust. Here's some other examples, and these are increasingly distant sources. This is Cygnus A, the brightest radio object in the constellation Cygnus. And what you have here is a galaxy spitting jets out in two directions, and it's kind of perpendicular to the line of sight. So we see one blob going off to the left, one blob going off to the right. That central dot would be the accretion disk around the black hole, and then you see how collimated it is. Incredibly, incredibly collimated. But as it goes up, that material moving at about 10% the speed of light is piling up gas and dust as it goes, until eventually it has a hard time continuing to go forward. It's like a snow plow that's plowed too much snow. It starts to slow down, and then the gas will expand in other directions, giving you this giant cosmic Q-tip structure. This is another version of that, but this one's pointed at you. This is Virgo A. You don't have to remember all these names. This is just by way of introduction to the rest courses and emission mechanisms. We have two jets. One is pointed almost towards you, and one's pointed away. Now these jets are moving relativistically, some reasonable fraction of the speed of light, 10%, 20% the speed of light. And so relativistic effects come into play. And we talk about those in 102. But one of those effects is a brightening effect. If something's moving towards you near the speed of light, instead of emitting its light in all directions, that light gets funneled into its direction of motion. So one jet is incredibly bright. You can see that one's kind of coming at you. The other jet you don't see until it slows down and poops up. And then it's emitting in all directions. So what we have here is a jet moving kind of towards you, and then the jet that's moving away we don't see. It's made relativistically dim until it slows down, poops up, and emits in all directions. And here it is in the optical. This one is so powerful that even in the optical, if you look near the core anyway, you can see the jet. And in this Hubble Space Telescope picture, you can really get a feel like that jet does feel like it's moving towards you. You can see how it expands with its scale. But the other jet you can't really see. And then I think this is the last object. And this is something called a quasar. This one's called 3C273. It was never given a fancy name. It's kind of faint. The quasars, we don't see too many in the current universe. But if we look back over great, great distances, which is looking back in time, since it takes light so long to get to us, we start to see these objects. They're among the earlier objects in the universe. And these are probably the beginnings of the galaxies that we just saw. Galaxies forming, you have a black hole that grew really big, really quickly. It's being fed lots of stars and producing jets. And this is actually an optical image, and you can see the jet coming out of it. And we watch these things. We take pictures year after year after year, and we see the jet changing. Because the flow in that jet is so quick, the relativistic motion, that we can actually see the blobs change with time. And this is one of the nearby quasars, but there are many, many more the farther out you go. And mysterious early building blocks of what became the radio-loud galaxies in the modern-day universe. Here's a radio picture of that one there. You can see the blob coming out, coming towards us. So that's from nearby to far away. Tour of the universe there in the radio and the optical. Oh. Yeah, I know. There we go. So any questions about that? It's kind of the conclusion of radio astronomy. I talked a lot about it. As I said, I really like it. I talked about the telescopes. I talked about the emission mechanisms, which you need to know. And it also, as I said, serves as an intro for the rest of this course within the solar system and the next course from stars on out. So any questions?